Alright, we left off with Henry's law. So we'll start with immiscible liquids. And this immiscible simply means solutions which can't mix together, or we cannot mix uh, immiscible liquids. Means suppose, for example, oil and water, they are immiscible liquids. Even if we put them together, they don't mix up. So they are called immiscible liquids. And vapor pressure of such liquids, uh, vapor pressure of immiscible liquids are totally dependent on the independent pressures. Means suppose there are two solvents, A and B, and if we mix them together, the total vapor pressure will be equal to the partial vapor pressure of A plus the partial vapor pressure of B, of the pure solvents. Because see, since they don't mix, they exert different pressures, or when it comes to the pressure exerted of the container. Therefore the total pressure will be equal to the sum of the individual pressures, or we can say like the ratio is also P naught A over P naught B, number of moles of A over number of moles of B. So, and we can even address the weight of each of the individual solutions. So if we add weight, then the weight of each of the solvents is nothing but the molar mass, number of moles, and the molar mass of each of the individual solvents or solution, which makes up the total solution. So now we can relate it to the vapor pressure as well. P naught A MA over P naught B over MB. So that's how they're related. But if the liquids are miscible, that means if we can mix the liquid easily, then they they are governed by Raoult's law. Raoult's law. Because in the event of the two solutions mixing together, if they mix, then it becomes a different solution. So the vapor pressure now depends, according to Raoult's law, depends on the mole fraction of the solution, which simply says now P is directly proportional to the mole fraction, the pressure of the solvent A will be directly proportional to the mole fraction. That's what within the mixture. That's what Raoult's law states. So now the vapor pressure, the vapor pressure of the solvent will be equal to, if we change this proportionality sign, then we can add the vapor pressure of the pure solvent. So that's similarly, if it's a mixture between two components like A and B of miscible solution, then the same goes for the component P also. B. I mean, now if the composition, if we are to determine the composition of the vapor phase, then uh, okay, we'll try to derive it. All right, now if we take y sub A as the mole fraction of A and of A and vapor pressure in vapor phase above the solution, and YB sub B as the mole fraction of B in vapor phase above the solution, then according to Dalton's law, partial pressure for the pressure of A, it should be the mole fraction into the total pressure. And so from Rolle's law, we've just derived that the partial pressure of A is equal to the mole fraction into the partial pressure of A, the standard partial pressure of A. This means standard partial pressure. Similarly, for component B, we can also say that it will be equal to the mole fraction of B and the standard partial pressure of B. So if we combine it, since if we combine these two mole fractions, if we add it up, chi A plus chi B, then we simply get, and one thing I have to tell you, the mole fraction of any solution, suppose of component A and B, component A and B will always be equal to unity, 1. So here also we'll apply the same, and then this chi A, if you manipulate this equation and put it, then we'll simply get ya t over p naught A and yb pt over p naught b. So that is plus is equal to so we can simply say that 1 over pt is equal to excuse me ya over p naught A plus yb over minus plus yb over p naught b. So this is one equation which we'll continue to use. Okay, here is a question of a miscible solution. Benzene and toluene are miscible. So at 300 Kelvin, the standard pressure of toluene is 30 millimeters of mercury, and the standard partial pressure of benzene is 100 millimeters of mercury. So the mixture is composed of 3 moles of toluene and 2 moles of benzene. So we are asked to calculate if the pressure over the mixture at 300 Kelvin is reduced. So if the total pressure, if the total pressure at the same temperature is reduced, then at what pressure does the first vapor is formed? And the second one is, what is the composition of the first trace of vapor formed? Third one, if the pressure is reduced further, at what pressure does the last trace of liquid disappear? And finally, what is the composition of the last trace of liquid? Now, you can pause the video and you can try and solve. For the first question, the answer is 58 millimeters of mercury. If you can calculate. So for the first question, at what pressure does the first vapor is formed? Now, we know that the total pressure is nothing but the mole fraction of the individual components into their standard vapor pressure. So there are two components. So we'll add the two components, the sum. So and then we know that the moles of toluene is given to be 3 moles, and moles of benzene is given as 2. So if for benzene, if we for toluene it's given as 3 moles, and for benzene it's 2 moles. So mole fraction of toluene will be 3 over 3 plus 2. So it will be 3 by 5, and then for benzene it's 2 over That's how we calculate the mole fraction. So we'll just add those values there. So, and then the standard partial pressure, the standard pressure for the component A for toluene, we will use PA as toluene, so it's given us 30 millimeters of mercury. So just put the mole fraction into the pressure given, and then for benzene, it's 2 by 5 into 100. That gives us to be 58 millimeters of mercury. So that is our first answer. Now the second part is about the composition of the first trace of vapor formed. So as we have calculated just now, the individual composition of vapors. So for benzene, Y of benzene will be equal to the mole fraction of benzene partial pressure over the total pressure. So it's equal to 2 by 5, the mole fraction into, we have calculated the total pressure to be 100. Sorry, we have calculated the total pressure to be 58 millimeters of mercury, and the standard vapor pressure of benzene is given as 100. So that gives us the value of 20 over 29. And then for similarly for Y toluene, you calculate the same analogy. You get 9 over 29. And for the third one, if the pressure is reduced, so at what pressure does the last trace of liquid appear? So similarly, the third one, 1 over P is equal to YA over standard pressure plus YB over standard pressure of B. So which is equal to YA 20 by 29, right? Sorry, 9 by 29. So 3 over 5 into 100 plus 2 over 5 into 30. This is 100. This is 30. So that gives us P is equal to 65 to 50 millimeters of mercury. So pressure would be nothing but 250 over 6 millimeters of mercury. So at that pressure, we'll see that the last trace of liquid disappear. And the last one, the composition of the last trace of liquid. So for spiral benzene, it's given by Y of benzene into the total pressure over the end of benzene. So let's divide 5 into 256 upon 100, which gives us 1 over 6. And you will do the same for toluene. So the applications and limitations of Rolle's law are given in your book. So I suggest you go through it. And this Raoult's law is is for an ideal solution. So there are ideal solutions, the difference between ideal and non-ideal solution. If a solution obeys Raoult's law, then it's an ideal solution, and if it deviates from Raoult's law, then it's a non-ideal solution. Thermodynamically, we'll try to explain what's the difference between an ideal solution and a non-ideal solution. Now, for an ideal solution, the enthalpy of mixing is always equal to zero, and the change in volume of mixing is also equal to zero. That means there's no change in volume. Suppose, for example, if you add 1 liter of a solution plus another liter, then it will give you 2 liters. It won't. It will. It will be. It will be equal to the amount of added volume. It won't change. If it changes, then it's a non-ideal solution. We shall see to it. And then an ideal solution, as I mentioned, it always obeys Raoult's law. But if it's a non-ideal, this is for ideal solution. But if it's non-ideal, then you should see that the enthalpy of mixing is also not equal to zero. It may be negative, or it may be it will show positive deviation or negative deviation, and the volume change in mixing is also not equal to zero. That means if you mix 1 liter of a certain solvent and another liter of another solvent, then it may not add up. So that's the difference between ideal and non-ideal solution. And we have another type of solution which simply we call the azeotropic mixtures. Azeotropic mixtures. Now these azeotropic mixtures means this type of solvents show very large deviation from ideality. That means the azeotropes are liquids which have very close uh, boiling points. So if you try to distill this type of azeotropic mixtures, they distill over as the same liquid. I mean the two components, they distill over together because their boiling points are similar, close, very close to each other. So the azeotropic mixtures are separated by usually by fractional distillation, where we monitor the changes in the boiling points accurately to a better accuracy. All right, so we'll move on to colligative properties. These are the properties which are dependent on nature of particles and are uh, like the constitutional properties like electrical conductance and so on. So there are 4 types of colligative properties, namely the relative lowering in vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. And another abnormal colligative properties are governed by Van Hoff correction. So we'll see to that later. Now, let's discuss one after the other, the 4 different colligative properties. So, for example, like if you add common salt, sodium chloride, to ice, then the temperature of the ice gets lowered to negative 10 degrees Celsius, which is very low compared to the temperature of ice. But even if it goes negative, below zero, negative to negative side, but you'll see that the ice melts even though it's very cold. So you understand that it's because of the colligative properties. All right. Okay, relative lowering. First one, relative lowering of vapor pressure. What does this mean? Now, you'll notice that uh, if you add any solute, any type of solute to a solvent, so suppose you are boiling water and you add tea leaves there, then the after adding the tea leaves, it boils faster than the normal. Uh, it takes lesser time to boil than if you're boiling only water. It's because of the addition of that solute, that is our tea leaf in this example. Now it's due to the relative lowering of the vapor pressure. If you once you add a solute, the vapor pressure of that component of that solvent is disturbed. It will no longer behave as a pure solvent. So since that vapor pressure is disturbed, so it may boil easier, or in the case of you adding tea leaf to water, or it may boil at a later stage because of the relative lowering of vapor pressure. So mathematically, the relative lowering of pressure is equal to the mole fraction. So P naught A minus PA over P naught A. So that's our mathematical expression. We can also express these in terms of molar mass. So molar mass of that solute will be equal to the weight into. These are some of the expressions which we need to keep in mind, so that while working on numericals, this equations comes in handy. So here's a question. We calculate the weight of urea that must be dissolved in 400 grams of water, so that the vapor pressure is lower 2% by 2%. So if the let our vapor pressure be P naught for water. So P naught minus the pressure of the solvent is equal to 0.02 volume. So our solvent will be equal to 0.98, which implies 0.02 over 0.98 is equal to W over 60 into 18 by 100. 400. So here W is the weight of urea. So weight of urea given by 2 into 60 into 400 over 98 into 18, which gives us grams. So 27.2 grams. So 27.2 grams of urea has to be dissolved. Here's another question. So we're asked to calculate the also creating the mass of the solute. Mm, so you can try to solve on your own. Mm, we know that P naught minus the standard pressure minus the pressure of the solvent is equal to our weight and the molar mass over weight. So the molality, calculate the molality. So the pressures of the individual pressures are given. Then two mass is also given. Weight, mass, molar mass is also given. So we just plug in those values. 283 minus 271 over 271, then over m, that will be 2 into 58 by 80, so 163 grams per mole. Okay, so here are two questions. So this is an assignment for you. You have to submit it before 4th of this month. And I've given you my WhatsApp number, so you solve it in an A4 sheet and then submit it to me before or latest by 4th. We'll continue with the rest of the collocative properties in the next video.